Hello, my name is Morris Yao, and I'm here to talk about list decodable subspace recovery. This is some joint work with Prasad Raghavendra. So our question is, can we develop algorithms for estimation, learning, and optimization that are robust to an overwhelming fraction of untrusted data? Our setting is we are presented with n data points in d dimensions drawn from a distribution D. An alpha-agnostic adversary inspects the dataset, removes and replaces 1 minus alpha n data points, simulating a 1 minus alpha total variation shift. Our goal is to recover statistical properties of D. For example, if D lies in a low-rank subspace, we'd like to recover the subspace. So the subspace recovery problem, we have some data, it lies in a low-rank subspace, which we call P, and we want to find P. Now, how would I do this? I'd use PCA, but what's the problem? PCA fails in the presence of outliers. So there's been a long line of work, and this is a very old problem on how to do robust subspace recovery, and I can't go into it. The focus of this talk is what happens when alpha is less than a half. So recall, alpha is the fraction of clean data, of inliers in the data set. So now we're in the setting of overwhelming adversarial outliers, and taking a look at a prototypical data set, this seems to be a little hard, but in fact it's impossible because the adversary can actually set up all the outliers in a subspace that is very far from P. Therefore, recovering P is impossible. But what one could hope is to recover a succinct list of subspaces, one of which is close to P. This is analogous to list decoding and the theory of error-correcting codes. Now, so we're going to take this prototypical example and keep it in our minds for the rest of the talk, and we'll be constantly referencing it. So our formal setting, P is a rank K projection matrix. Our data is x1 through x alpha n, drawn normal 0 P, a degenerate Gaussian for alpha less than a half. Our inliers are the x1 through x alpha n, we call them I, and the outliers, we call them Q. The outliers can be adversarially chosen. A minor note, this is a little different from the total variation adversary, but all of our algorithms work in both settings. This is just a little easier to write on a slide. Our result is we have an algorithm that recovers a list L of length O of 1 over alpha of projection matrices such that there exists a pi in L satisfying P minus pi, and Frobenius norm is upper bounded by big O of K eta over alpha to the fifth with high probability in D, where eta is a tunable parameter. Our sample complexity is n equals K to the big O of 1 over eta to the 4. Our runtime is n to the big O of 1 over eta to the 4, which, if you want to achieve some constant correlation with P, you set eta to be some polynomial 1 over alpha, and this is some polynomial time. So there's some concurrent work by Kotari and Bakshi, and they're able to take this K dependence in the recovery guarantee down to log K in quasi-polynomial time. It remains an open question to remove the K dependence in polynomial time. So, this list decoding, list decodable robust statistics has been done in a variety of settings, in mean estimation, in regression, and subspace recovery now. You can actually apply this notion of recovering a list to a overwhelmingly corrupted data set to pretty much any statistical model you can think of, and I highly encourage you to look at this, and this is a very interesting body of work. It turns out also that list decodable learning is provably equivalent to something called semi-verified learning. The key insight here is that it is possible to output the best estimator in the list given an additional log 1 over alpha independent samples from the inlier distribution D. So when you want a single estimate instead of a list, all you need is a few more data points as side information to find the single best estimator. The motivation is that although it is resource intensive to ensure the cleanliness of a large data set, it is often easy to independently collect or audit a few inliers. Think Yelp reviews, it's easy to collect some genuine ones. And also there are some applications of list decoding to mixture models, and I'm not going to talk about it. So let's come back to subspace recovery. Can we design an inefficient algorithm for list decodable subspace recovery? So let's try starting from an inefficient approach. So to start, we're going to use what we call the sum of squares algorithm design paradigm. We're going to write down a system of polynomial inequalities. We're going to assume oracle access to a polynomial system solver, and we're going to design an algorithm. Our task then is to write down a set of polynomial inequalities with only big O of 1 over alpha solutions such that P is amongst the solutions. So let's take a look at our prototypical example again, and let's try to think what kind of inequalities I'd have to write down such that the solution to this set of inequalities will give me P. And it turns out that this is pretty much the answer. Consider the following system of equations: R over indeterminates W1 through Wn in 0, 1, and pi in Rd by d. Here, W1 through Wn, they are meant to indicate whether a data point is an inlier or not, and pi is supposed to be the projection matrix that is P. So let's look at these constraints or these equations. I use them interchangeably, and they're going to appear on the next slide anyway. So we need to check two things. The first thing is that the assignment where wi is equal to 1, if the ith data point is an inlier and 0 otherwise, and pi is equal to p, is a solution to R. So this is a feasibility check. So indeed, of course, the first constraint is that wi is in 0, 1. So that's true. The second constraint is the sum of the inliers is alpha n. That's also true. The third, fourth, and fifth constraint force pi to be a projection matrix, where we introduce these variables v1 through vk to be an orthonormal basis set for pi. And of course, p is a projection matrix, so the constraints 3, 4, and 5 are satisfied. The final constraint is if wi is 1, then xi is going to be equal to pxi. And this is true because xi, if it's an inlier, lies in the subspace spanned by p. Right, but there's a problem. There can be more than big O of 1 over alpha solutions to R. In fact, there can be an exponential number of solutions. So this seems to be a bit of a problem. Even if I had Oracle access to a polynomial system solver, it seems like I can't solve this problem yet. Right, so to talk more about this, I'll have to introduce some of the nuances of this polynomial system solver that we have access to. So of course, solving polynomial systems is NP hard in general. The sum of squares is a hierarchy of algorithms that solves increasingly tight approximations to polynomial systems, and the output of the sum of squares algorithm can be interpreted as pseudo-distributions over solutions to R. So think about a solver that outputs a solution to R. That seems hard. It is hard. And if you output a distribution over solutions to R, that seems even harder. But if I output a pseudo distribution, this turns out to be computationally tractable. So for the rest of the talk, I'll be using the word pseudo distribution. And when I do so, please just pretend I'm saying distribution, and most of the understanding still goes through. Right, so what is a problem with finding a distribution, mu, over solutions to R? Well, this could happen. We could place all the mass on a subset of the data comprised entirely of outliers. So here, maybe I put all my mass on this yellow subspace instead of the subspace P, where the blue, the blue data is. And so how do we deal with this? We desire mu to be high entropy, placing probability mass on all solutions, so I'm not, missing one solution or another. Right, so how do I ask a distribution to be high entropy? Well, here's a proxy. Let mu hat be the distribution over solutions satisfying R, minimizing the sum of squared marginal probabilities of W1 through Wn. Let W pi be a random variable sampled from mu hat. Then the probability pi is equal to p is lower bounded by alpha over 2. And this suggests a very natural algorithm. What we should do is we should sample from this high entropy distribution mu hat. And if I sample, then I'm going to get a pi that is equal to p with reasonable probability. And indeed, that is our algorithm. Algorithm iteratively sample a list of solutions from mu hat, w pi 1, w pi 2 to w pi O of 1 over alpha. And we output the list L, which is just a list of the projection matrices we have sampled. And a natural corollary, with constant probability, there exists a pi in the list L where pi is equal to p. So this seems to be, at least as an inefficient algorithm, this seems to work. Of course, you might notice that there are some problems if I want to make this efficient. First of all, how do I sample a list of solutions from mu hat? Right, so it turns out that working with pseudo-distributions, we only have access to the low-degree moments of pseudo-distributions. So how do we simulate sampling given only access to moments? So here's a start. We hope to output the expected estimator, the expectation of pi under mu hat. Now this doesn't work because the variance of the estimator can be large, indicating heterogeneity in the distribution. In this case, the expected estimator can be far from p. So let me illustrate this with an example. Let's say this is my data set. Let's say the two subspaces that are solutions to R are P and P prime. Let's say I put half of my mass on P and half of my mass on P prime. Then the expected estimator, expectation of pi under mu hat, is 1/2 times the identity, which is far from both P and P prime. And as a side note, it's not even necessarily a projection matrix anymore. So how do I fix this? Well, here's a plan. I could just pick a random xi. I can take its corresponding indicator variable wi, and I can fix it to be equal to 1. So I fix that to be, I believe that to be an inlier. And if I do so, then I should be able to isolate the solution that is this subspace P upon which the blue data lies. Right, so here's the natural algorithm. Repeat the following procedure O of 1 over alpha times, sample I and n with probability proportional to expectation of wi under mu hat, and append the conditional estimator, expectation of pi given wi equals 1, to the list. And this algorithm is computationally tractable if I replace every expectation with a pseudo expectation and every mu hat, which is a distribution, with a pseudo distribution. Right, so this is the full algorithm. So let's take a step back. As an observation, the recipe for list decodable subspace recovery via solving for high entropy distributions to polynomial systems and sampling through conditioning is entirely general. Now, in what statistical settings is list decodable learning possible and computationally tractable? Towards these ends, we develop a polynomial optimization criterion for list decodable robust statistics, which we call certifiable resilience, capturing state-of-the-art guarantees for mean estimation, regression, and subspace recovery. So first, we need to talk about what a generalized list decoding problem is to talk about what certifiable resilience is. So we are given a data set H that's comprised of data x1 to xn in d dimensions. We have a contamination parameter alpha less than a half, and a loss function phi of x theta that takes as input a data point x and a parameter theta in a space V. Let theta star in V be a target parameter achieving 0 loss on a set of inliers. Of course, we don't know what the inlier set is. So we can specify a generalized list decoding problem as a 4-tuple, HV phi alpha. Data set, parameter space, loss function, contamination parameter. So the definition of certifiable resilience, we say a generalized list decoding problem, HV phi alpha, is delta R certifiably resilient if V can be the parameter space, can be specified by a set of M polynomial inequalities, and the following polynomial system, R, can be used to show that theta is close to theta star via a degree R SOS polynomial identity of a restricted form. So let me kind of unpack that for you. Let's take a look at R first. It's composed of like 4 constraints. The first one is that wi has to be an indicator variable. The sum of the inliers has to be alpha n. That's the second one. The third one is that on the inlier set, the loss of theta star is 0. And the last constraint is that theta has to be inside the parameter space V. So for subspace recovery, the second to last constraint is we choose phi to be like the Frobenius norm. And the last constraint is just the projection matrix constraints, where you have to decompose pi into a sum of its orthonormal basis set. Right, and so one last point. What do we mean by a degree R SOS polynomial identity? So think of the degree of the proof required to prove that theta is close to theta star as a measure of the complexity of a computationally tractable algorithm for finding this proof. So this computationally tractable algorithm, the sum of squares algorithm, will take time exponential in R to find this proof and output, a list for our list decoding algorithm. So, whatever that means, we have the following theorem. If a generalized list decoding problem, HV phi alpha, is delta R certifiably resilient, there exists an ND to the O of R time algorithm that with probability omega of alpha outputs a parameter theta in V such that theta minus theta star in Euclidean distance is upper bounded by delta over alpha squared. And it turns out this generalized list decoding theorem applies for list decodable mean estimation, regression, and subspace recovery. And we hope that it has further future extensions. Right, so takeaways. It is possible to efficiently search and sample from distributions over non-convex polynomial systems and high-dimensional statistics. Subspace recovery in the presence of overwhelming adversarial outliers is possible and computationally tractable, and there exists a general polynomial optimization criterion, certifiable resilience, for the computational tractability of list decodable learning, subsuming state-of-the-art guarantees for mean estimation, regression, and subspace recovery.